All right, so we were talking about kinetic friction and static friction. So on the same surface, static friction will always be more than kinetic friction because of the bonds that build up as the object is at rest there. It's why it's always harder to get an object, to start an object moving, than it is to keep it going. If you're pushing an object, you have to give it a really big push to get it started, and then once it's moving, it's easier to keep going. It's because you've broken those bonds and now you've moved to kinetic friction. Okay? If in a question it says you push on an object and it just begins to move, it means you are just at the tipping point from static friction to kinetic friction, but you're still using static because it's just about to move. Okay, so back for kinetic friction, one other thing is the surface area that is in contact does not affect the kinetic friction. So if I had, I'd say a book, but it won't fit under here. If I had my calculator and I slid it like this, or I slid it on the side, assuming the surface was the same, the amount of friction would be the same between the two of them. Why? Because both static and kinetic friction obey the Fun law, Ff equals mu Fn. And nowhere in this equation does surface area come into play. Also, the amount of kinetic friction doesn't change if I slide it slow or if I slide it fast. The amount of static and kinetic friction, well, kinetic, because static doesn't have a speed. Kinetic friction is not dependent upon the velocity of the object. Okay, and both of them use friction, and I want to put an R there because I have for years. FFR, or F of friction, is equal to mu Fn, the Fun equation. Okay, there is a third type of friction, and the third type of friction is called fluid friction. And when we talk about fluids, you should know, I think from chemistry, that fluids are both liquids and gases. So this is friction that occurs in liquids and gases. The two most common types of fluid friction are air resistance, which we've already talked about a little bit, and water. Okay, resistance. Those are the two most common types. Now the thing with fluid friction is that it does depend, the amount of fluid friction does depend upon surface area. It depends on shape, and it depends on the speed of the object. And because of this, fluid friction does not obey the equation friction equals mu Fn. In actual fact, for every scenario, you almost have to develop a new equation, right? So like if the surface area changes, it's a different equation than if the old surface area that it was. So there's not a one-size-fits-all equation for this. And actually you would need calculus to do this. And so we don't learn a formula to calculate fluid friction other than we could do the sum of the forces to find it, right? If we knew the other forces acting on the object, we could find fluid friction from that. Now going back to prove to you that fluid friction depends on surface area and speed and stuff, imagine driving down Main Street, where you're in the passenger seat, of course, and you put your hand out the window. And so you put your hand out the window and you can feel the friction, the air resistance on your hand, right? If you turn your hand to the side like this, you don't feel nearly as much because the surface area and contact has changed. Okay, so it's definitely dependent upon surface area. Now imagine that you're still in the passenger seat of that car, but you're on the Trans-Canada Highway driving to Moncton, and you put your hand out the window. Clearly the amount of fluid friction you're going to feel going at 110 kilometers per hour is very different than the amount you're going to feel when you're going just 50 on Main Street. So it definitely depends on speed. It definitely depends on surface area. It also depends on shape. You think about models of cars. They're always streamlined, or shapes of airplanes and stuff. We streamline them to try to cut down on the amount of air resistance they're going to have. The faster an object goes, the more fluid friction it experiences. It's why the fastest runners, bikers, swimmers are bothered most by fluid friction. It's why Josh Phelps from the US paid big money, got sponsors for big money to develop a swimsuit that would cut down on the amount of fluid friction because he was so fast it was bothering him more than others. It's also why, like in bikers and runners, the fastest ones will stay behind the pack for a while and let the front ones get most of fight the fluid friction for them until it's time to make their break. Okay, so the three types of friction: static, kinetic, and fluid. Oh, one more thing about fluid. It's with fluid that we arrive at terminal velocity, right? So imagine I'm dropping an object off the top of a building. Okay, when it first starts to fall, gravity is pulling it down, but the air resistance, which will be acting up, won't be very big because its speed isn't very big. But the further it falls, the faster it goes. Gravity stays the same, but because the faster it goes, the bigger friction the air resistance gets. And there will be a point when its speed is big enough that the air resistance will exactly balance out the acceleration due to the force of gravity. So the acceleration will now be zero because the sum of the forces will be zero. That doesn't mean this object's going to stop. It just means that it's now going to fall at a constant speed the rest of the way down. So it's called terminal velocity. Terminal because it's the highest velocity that you reach, not because you are going to be terminal by the time you get to the ground. Some people will say, well, what is the terminal velocity? Well, it depends on the object. It depends on how the object is oriented, right? If you jump off the top of a building and you spread eagle like this, your terminal velocity is going to be different than if you're doing like a perfect dive, or if you're going in jumping off a diving board. If you spread eagle and land flat on the water, or if you go straight in, your terminal velocity will be different depending on the shape. Same for like a sheet of paper. The terminal velocity when I drop this sheet of paper like this is very different than if I crumple it up. Okay, so terminal velocity will be different for different objects. All right, so it's time now to do some questions. And I did give you some examples, and that's what we're going to do. But first I just want to talk about how we're going to do it. Okay, so you're going to draw your box, and then you're going to draw in all the forces. So gravity will always be acting down, Fg. If this is my surface, then there'll be a normal force acting up perpendicular to the surfaces. If I'm pulling the object or pushing it level with the surface, there'll be an F going this way. If friction is acting, it will be acting opposite the motion. So we put in all our forces. And then there are 3 steps to doing these problems. One step is doing the sum of the forces in the y direction. Okay, and if this object, this box sitting on the surface isn't moving in the y, then MAY will be 0. And what are the forces? An Fn going up, an Fg going down. Usually we call down negative. So when we do the sum of the forces here, it tells us that Fn is equal to Fg, and we know Fg is mg. So if we knew the mass of this object, like 10 kilograms, then we could get our normal force. Okay? Usually, as long as there's friction, sum of the forces in the y direction is where we usually start. Then our second step varies. If we were told the mu, then we would use that normal force and we would calculate friction. But some questions ask us for mu, and so if we're solving for mu, then you go to the second step, sum of the forces in the x direction. And in that, it would be the force you're pushing with going one way, friction going back is equal to max, and you would solve this for friction, and you would get the value. And then once you get the value for friction and the value for the normal force, you would come back to friction equals mu Fn. So this third step, depending on which route you go, it could be sum of the forces in the x is equal to max, or it could be friction is equal to mu Fn. So which route you go depends on what you were given in the problem. Okay? But it's usually always those